Okay, so this topic was one of my hobbies, and it gradually developed into a passion, and then at this point, it becomes more and more like a profession now. It's called the benchtop manufacturer in science lab. Basically, I will talk about how do you actually make things in your lab and then build modules. My previous presentation, I talked about imaging of SEI of lithium battery in oxygen-free environment, and that was a very difficult experiment. That's because we have to do the liquid cell construction and then make all the electrodes, and then everything has to be operated in a oxygen-free environment. In other words, you have to wear a thick glove, and all these small parts become very difficult to handle. Yes, I'll skip these and get to this point. So this is what the sample stage and liquid cell look like in the original design of atomic force microscope. And a lot of the AFM liquid cells look very much the same. They're small parts, and which makes it very difficult to operate wearing thick gloves. That's how I started to construct the liquid cell that is more easy to handle. And that at that point, I could not operate very complex designs and complex machinings. So everything is just circle and square. And that was 2014. And after 2014, I started to get into benchtop manufacture. Basically, I need to make something because the companies are not making them. All these liquid cell designed for electrochemical reactions, and then it was not very practical. That's because the electrochemical reactions using different electrodes that have different shape and size and thickness. So we have to design and build the cells of different size and shape. That's how I started, and we'll skip it. This is basically last week, right? We observed the SEI, and we later we designed and built a lot of electrochemical cells of more elaborate designs. And for example, this design and can be assembled with very much gloved hands and so on and so forth. Okay, I'll go forward quickly. This leads to the second part of it. This is actually a high school class I was teaching to a high school student in China. They want me to teach them about creativity because, as you can see, that in this global competition, creativity is very key. And they asked me to teach creativity. And then here, the Chinese words here says 3D desktop manufacture. The red word says to make, to create. What does it mean is that if you want, I tell the students that I could not teach you creativity. I cannot teach you how to create things because that's if I can teach you, I can create for you, right? You have to have your own creativity. However, I can teach you how to make things. If you know how to make things, you can make it differently. And then you can make it to fit a problem that you're witnessing. And therefore, you could create your own solutions for your own unique problems. And 1,000 people have 1,000 problems and have 1,000 creativity. By solving a particular needs and by the way of production or manufacture, you can create your own products. So that Chinese word says from make to create. You have to be able to make. If you don't know how to make it, you don't know how to create it. That's a fact. Or you have to have other people to create for you. So you need to be able to communicate with people who can make something. Okay. All right. So from create to make to create. Here the Chinese words here says that where to find most creative people. I don't have to mention the Chinese words under each picture's name because we all know them. Einstein, Wright brothers, Steve Jobs, Bill Gates, and then the one on the lower right corner, that's the Chinese gentleman who created paper. Okay, so these people has something in common, right? The upper right pictures, people who created gunpowder. There's something in common. All these very creative people, they're not professionals, all them amateurs. And that's my observation. All the most creative people, they're amateurs. They're not professionals. And the reason is actually simple. That is because they're very creative. They created a profession that did not exist yet. Why you cannot buy an Apple computer from a computer store when Steve Jobs created Apple computer? Because his computer, Apple computer, was sold in bicycle stores. That's because that computer store did not exist yet, or the amateurs. So if there is no such professions called creativity. Creativity is basically when people have problems and they solve the particular problems with a solution. And some of the problem is so ahead of the time, people create something that was never seen before, like aircraft. Okay. Let me skip these. So basically what the message of this presentation is that everybody can create things. Everybody can use these tools. Here is a little bit the perspective here. Here's a lot of things that you can find on internet. These are called 3D printed objects, and then people naturally thinking 3D printing is the benchtop manufacture. However, as I can tell you that is not all of it. It's just a small part of it. The 3D printing is a small part of the benchtop manufacture. Here a little bit of history. These are the in the Chinese textbook. These are the four greatest inventions of the China that contribute to the world. We had the creativity of paper, printing, and gunpowder, and then compass. And that's the four biggest creations of the Chinese history. And then the two of them are actually about spread of information, creating of paper and creative in printing press are basically the technology of spreading knowledge. Okay, so this is what the paper was created, or the book were created many years ago. You need a factory to print these things on a bunch of paper and therefore make a book. So book is a product made out of paper and then press on the machines. Okay, and this is how products were created. Products are created in these gigantic factories with big machines, and that's what the modern industries, modern manufacturers is. Now in 2000, no, not 2000. I think it's 1980s when I was in school. There were a revolution happening there. Okay, the picture in the middle, lower part is a printer. There were a revolution. It's called desktop printing. Okay, desktop printing. You can create a book by receive the information of the book, which is the digital copy, and then you create it. Before this revolution, a book is a product. If I want to give you a book and I lose the book, you have the book. However, after this, a book is no longer a product. After this, the book is a piece of information. I can give you the book, you print it out, I did not lose my book. And I think the same thing is happening in manufacture. Many years ago, manufacture is done this way. People are hammering away the particular parts, and then, or in the factory, the products were assembled. Okay, that's how manufacture is done. And then this is a modern machine. This is called CNC machine. It's computer numeric control. This is basically it's a reverse of the 3D printing. It's a 3D cutting that you start with a piece of material and then you computer control a tool and then cut away the material you don't want. And this is completely computer programmed. And then you can create a different product by receive a code, a computer code. So this is a modern manufacture, and this machine is very expensive. However, if you look at this, it has XYZ movement and they have a spinning tools. And that's the whole thing can be recreated in a small scale, and we call the amateur CNC, computer numeric control. Okay, the picture on the right lower corner, this is a CNC. This is a picture I downloaded from eBay. So this is an amateur CNC. This machine is priced at $2,000. There's something that's even cheaper that you can buy them for less than $1,000. With the help of this computer numeric control mill, you could produce small products. And of course, I mean, 3D printing also create small products. Okay, so as soon as you have these computer controlled production tools, the product is no longer a product. The product become a piece of information. In other words, I could email a code and you use this code, and you can create the product by yourself. Okay, so that's the modern revolution. I think it's happening going on. It's called a desktop manufacture. You can manufacture your product on your desktop. 3D printing, that's a very common topic. In 3D printing, there's many different technology. This is the most simple, widely used technology. It's called extrusion. Well, extrusion is that basically it's like a tube of toothpaste, and you squeeze out the softened plastic, and plastic will be hardened when the temperature is cooled and form a three-dimensional object. And the part can be built layer by layer. There are different kinds of 3D printing too. Extrusion, and then you can have a metal sintering. Basically, it's a metal powder, and then we use high temperature focused laser to solidify powder layer by layer and build a 3D metal parts. Or you can have polymer chemistry to solidify a polymer from liquid to solid and form a three-dimensional subject. So these are 3D printed parts, and then you can create anything, almost anything you can design. Okay, but there is 3D printing material does have its own drawback. The biggest drawback is that basically you cannot choose the material. You have to accept the material it provides to you. So that's the drawback. The advantage of it is unlimited size and shape, not like the CNC machine. You have to have a certain particular shape. When the shape is too strange, it cannot be made. Okay, and there's another type of benchtop manufacture. It's called the CNC laser. This is a CNC laser. Basically, it's a printer, but using a laser beam. And if the laser is have a short pulse with low power, basically it can write things on the surface of a material. And if it's powerful enough, it can cut through. So let me tell you a story of this laser CNC. Okay, so this is on the right hand side. It's a clock that's hanging on the wall of my friend, and I said, "Oh, that clock is very good. Can I have it?" And he said, "Yes, I will email it to you tonight." So he emailed the design of the clock tonight, and I penned this. They call it G code. Put it on a CNC laser. It cut the parts out, and then we assemble into a clock. Okay, so at this point, when we can produce things out of computer code, the G code in this case, a product is no longer a solid product. The product becomes a piece of information, and if I give you my product, I don't lose that product. Basically, I both of them own the product. The manufacturer is no longer limited to the factory. As a matter of fact, if you have this CNC, a computer, you can manufacture yourself. Okay, so this is a video I saw in 2013. That's how it got me into the CNC production and CNC mill. It's amazing that with 5-axis CNC, you could carve a statue out of a block of aluminum, and this is amazing to me. So I started to study it and then learn about all the programs and so on and so forth. The first thing I learned is the CAD, computer aided design, and this is computer aided design. There are many different kinds. Later I will demonstrate you how to design something that's very simple. Okay, so computer aided design, basically it creates as a three-dimensional part by from empty space. Okay, so anything you can think of, you can create. That's CAD. It basically turns something in your head into a drawing that is three-dimensional object. It is extremely useful. That's because we're chemists, most of us, AFM scientists. I don't think anybody need to absolutely learn how to make things. However, I think people need to understand how things are being made. And if you understand that, you could learn how things being designed, and then you could use the knowledge to communicate your idea from your head to a 3D space and communicate to the machinist or engineer that's something you want to make. I always joke, like, if you want me to draw a circle as a chemist, when I was just a chemist, If you want me to draw a circle, the circle will be not accurate, will be missing information. That's because we draw a circle, we kind of ignore the size, the precise dimension, thickness of materials, tolerance, and so on and so forth. But if you learn how to draw the CAD, you could optimize your design ideas, and you can you can communicate much better with an engineer or machinist, because most of us expect to have the machinist to build the parts we want to invent. Another observation is that we're scientists, we're physicists, chemists, or material scientists, and then when we have some smart ideas in the lunch break, we always put down our ideas on a piece of napkins, right? And then can I ask, did it happen to you? And then can I ask what happened to the napkins? And then a lot of people tell me though they lost the napkins because it's not being communicated correctly, or was did not recorded, and napkins get lost. With the CAD skill, you could turn them into something you can look at in a three-dimensional way, and then you could show it to people, optimize it, and so on and so forth. And it's kind of important. Now, a 3D drawing, it's always started with a sketch, and then you grow the sketch in a different way, extrude or rotate, and so on and so forth. And you cut things away as if you are cutting it with a curve, and then form a 3D object. Now, another computer software I want you to pay attention. It's called a CAM, Computer Aided Manufacture, CAM. CAM is actually extremely useful in learning desktop manufacture. Okay, CAD, you can draw anything. You can draw things that cannot be made. Okay, CAM actually it's a much better connection between your idea to a real world. It does not start with empty space. It started with a piece of material, and then you can cut things away. And when you cut things away, it will limit the size and shape of cutter to certain cutters that of certain specifications. You can actually buy them from tool companies or even from eBay. Okay, so this is an amateur CAM software. I'm an amateur, so I show you the amateur. It's a geometric V curve. Later, I'll show you how to design some very simple things and how things are programmed. Okay, so V curve, and then it started with circles and squares. See, this picture looks a lot of lines, but it's actually made of squares and circles. And then it's actually not even 3D, it's a 2D. And then on the right-hand side, you have these the specification of tools. In this case, you're using a 1/8 inch end mill, which you can buy them from eBay. And then this end mill will cut following a certain path, and then cut away the things you don't want, and then form a three-dimensional part. So you start that, and you define a certain depth, and then it even simulate the G code, and then this is what this part will look like. This is actually the real design of a liquid cell that I use to do the lithium battery research, lithium battery experiment. You can see there's a big square at the bottom. This big square has little cuts on the side. That makes very easy for you to grab with gloved hands, and so on and so forth. And this is the actual part. Okay, so what if you have a complicated shape that cannot be defined by a vector curve and a depth? And then the CAM can combine with the CAD. You can create a complex structure. For example, in this case, it's a little half hemisphere shape, can be programmed. This is a small the small other part module of this V curve. It's called a 3D something, I forgot. Yeah, and then the tool will carve the surface and then form a complex structure. In this case, this is the shape, and this is how I made this liquid cell for a contact lens. How do you make something that is soft? In this case, this is rubber seal. Okay, that's you have to combine different manufacture techniques. In this case, you can combine the CNC carving with injection mold injection, whatever we call it. In this case, you can buy these silicon material. They are basically liquid, two parts, and you mix the two parts together after 5 minutes. Some of the things is after 10, 15 minutes or an hour, it becomes solid. So all you need is create some kind of mold like this, and then mold it into this shape. And then combine these two, you can make the soft rubber part like this. Okay. This is Kelvin's truck, and he say, I want to do this truck, and then we digitize this, and then he's thinking 6 wheels is better than 2 wheels, so we made a truck that's 6 wheels. This is an example of it. Okay, so these are the examples. This is a transparent phone that I created for my daughter. Later she lost it. It's a little small size version of the iPhone, and it's iPhone 5. That was I spent a whole afternoon to make this. And this is a low temperature cryogenic AFM. This is my friend Ryan Murdoch. He built this entire thing, used his machine at home in his basement when he was still living in Michigan. He built this, and then now he's building an entire business. It's called Renaissance. He built an entire business using this skill by his own creativity, and he make those XY stage that can move as precise as 5 nanometers in UHV at very low temperature. I think his company is probably going to worth $100 million. So that's kind of a fun story of such creativity. The following a bunch of parts I created and designed for my collaborations. And this is a sample stage with a built-in LED, and you can shine LED light, and you can plug in the AC voltage, so you can modulate your LED illumination. Okay, the entire thing is out of plastic. That's because the machine at home that I have, I don't want to handle lubrication fluid and cooling fluid, so I stay with plastic. So this whole thing is made of plastic. This is a module that coupled with the optical fiber, you can shine a light onto the sample, and you can modulate the light. Okay, so that's the one example that I did. Some liquid cells, and this is sample modulator. I created for a professor in Case Western Reserve University. And this is a magnetic field adjusting our generator. In this gap, we could generate 1 Tesla, 8,000 gauss of magnetic field across this little gap by rotating this permanent magnet. Here's a motor on the side, there's a worm, and there is a gear. And this entire thing also I made in my basement. And there are many more examples of it, and I don't want to spend too much time. And if you have a question, you can ask me. And as we proceed, I'll show you some very simple examples of design and of something. Okay, go ahead and have unmute yourself, ask me questions. If not, I'm going
to hi, Song. This is Anvesha.
Yes.
Great presentation. I think this meeting is getting recorded, and you mentioned going over the sample heater design or suggestions for us. So I was just wondering if we can have the recording of this meeting from you.
Yes,
just this one. Yeah.
Yes, yeah. It'll be on YouTube. You'll find it. And
okay.
Yeah, and this is not going to be only one. I have lots of the old ones. Anyways,
yeah.
So I'll show you how to do that. It's not complicated. And then if you see how I did it, I'm going to send you that software, and you do it yourself. That's a way of communication. Is that instead of you drawing things on a paper, you drawing things on 3-dimensional, and you figure out all the things that you can change. Okay. So can you see the CAD drawings that I'm on my computer?
Yeah.
Very good. Yes. So this is something I just draw and for the last 20 minutes. This is a simple STM liquid cell. So this part is made of Teflon. I did not put the O-ring here because O-ring takes extra time to design, and we'll try to describe things as simple as possible. So this is a simple Teflon STM liquid cell. These 4 holes are for you to plug in the electrodes. Okay. So it made of 2 parts: the metal part and the Teflon part. Let me show you the ring part. Okay, this is the ring part. All right, and how it was made? How does it's joined here? See if I can show you this part. So basically, it's built layer by layer like this. Oops, it's not allowing me to do that. And first you have a sketch. Basically, it's a big circle, small circles, and a couple of circles, and you extrude it into this shape, and then you make another circle and extrude it. Just two part. The whole thing can be joined in 5 minutes. Okay, that's CAD. If you know how to do this, you can download some of the very simple CAD program. You just Google for, let's say, free CAD. Google has a Google SketchUp, and you can download it, and then you can draw these things, and you can draw it. And this is a good way to, first of all, it will ask you those dimensions, and you can get things more precise. And second, you can put into perspective. And then finally, you can communicate with me. Say, hey, I have design. Take a look at it. What do you think? Any problems, right? You can communicate. You can
Yeah.
change. Okay. Now, let me see, how do we make this? Okay, I will show you two different ways of making it. First is that I will produce a STL version of this file. STL is it's a particular version that you go to eBay. If you type in STL, you can buy an entire statue of very elaborate design for $5. Basically, you don't buy this statue, you buy this STL file. It's a three-dimensional file you can buy. Okay, so you save as, and then this is called ring, and then this is the STL file that you create. Save, and I already saved it, so I saved it twice. Okay. Yeah, yes. So this is saved, and I'm going to close this. I will open a different program and then show you how to 3D print it. Stop sharing. I'm going to share this slicer. Okay, I'll share the slicer. Okay. So this is a Creality slicer. This is the program I use on my 3D printer. And then you say here, open and load. Open. There we go. That is the 3D. Of course, you don't want to print this way, because when you print this way, it's need a lot of support material. The whole thing will just be a mess. So I need to rotate. So I want to rotate this. Grab it like bam. Okay, and then you tell it it's PLA, which is a material, and you want a very high quality, which is 0.1 millimeters, and it tells you it takes 9 minutes. And you say that's not enough. I need like I need lots of them. You can print an array of this. 9 minutes, 10 minutes. You can print this. However, can I tell you that this 3D created liquid cell is not going to work? Why is that? That's because use extrusion way of production. The part created has holes in it, and that's one. Second is it's PLA. You cannot use Teflon, and yeah, you cannot do that. Yeah, you can do the liquid cell, and you can try to use as mold. Many techniques you can do that, but if you want to create this plate, yes, you can, because it's a structure material. It doesn't matter you have holes there or not. Okay, so now let me show you a different way of making it. Let me stop sharing and show you the V-curve way. Close this. And where's my V-curve? Here's V-curve, and let me share the V-curve. There you go. Okay, this is the CAM file. CAM file, as I said, is the computer-aided manufacture. It started with a piece of material. It does not start with empty space. So let's see, create a new file, basically a new material. And I want to say 2 by 2 inch, and then thickness is 0.125 inch. That's because that ring I designed. No, it's not 0.125. It's be thicker than that, because it's 0.135. Let me think. What is the thickness? 0.125, 0.01. Yes. Okay. Let's do 0.15. Okay. Let's do 0.15. All right. Okay. Now you can see I'm already started worry about where do you buy the material, right? Because 0.15, you have to think about where to start with, right? You don't no longer start with empty space. Okay, now the ring, the liquid cell will be Okay, the inner circle is 0.5 inch, so it's 0.5 inch. And the outer circle is let's see, no, the outer circle is 0.5 and inner circle is 0.3 inch. Okay, and then you're gonna have 4 holes which allow you STM pin to insert in for ground wires. Okay, so here I have another circle, which is this little circle right here, and it is 0.015, actually 0.03. This is which is a millimeter. Okay, and it's not one. I need 4 of these, so I'm gonna have a circle 4 and around 1 and 1 because this is 2 by 2 inch, so the center is 1 and 1. I need the 4 items. Copy. Okay, so now, but remember that this whole thing is insert into the plate, so we have some edge that is thicker, so it does not go through.
Yeah.
So I need to go to larger one. At this point, my design is finished. Okay, so now I need to cut it. So this is the tool path. First of all, I need to cut in the circle. I need to cut this out. So this is a profile cut. I need to cut through this, 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 and this, and this. Okay, I need to cut these. And this is going to be inside cut, and I use a very thin cutter, cut through the thickness 0.15, so I need to cut 0.15, cut through. And the tool has to be small because you cannot cut something smaller than with a cutter that's bigger than the hole. So I need to have 1 millimeter end mill. Select and then calculate. Actually, this hole is too small. Let me increase this a little bit. Okay, so at this point, you already started to worry about the very practical things of the manufacturer. For example, the size of the hole, location of the hole, the tool fits, and then so on and so forth. Let me get all of these. Bye. Calculate. Still don't have it. I think the tool is still too big, so I need to choose a tool that's even smaller than that. I'm gonna make this hole even bigger. So just for the sake of it, because it create a tool parameter for a very small tool takes extra time. I don't want to waste your time looking for these things. And then one. Okay, now it's working. So this tool is gonna cut through it. Okay. And I'll copy, make another one.
Yeah.
Calculate. Okay. The next thing is I need to cut a shoulder of it. So it's gonna be outside this curve. So it's gonna be also profile, but instead of inside, it's outside. So this still a curve. It will cut is 0.125. That's how thick is the cut. And then I'm gonna use a thicker cutter and mill 1/8 inch. Select, and it will be outside. The thick is 125, and calculate. So this is gonna run through this. Oh, get it wrong. I'm cutting outside the round curve. It's need to be outside this curve. Okay, right. I need to regenerate this picture. Close. Okay, so let's do this later. And then I'm going to cut through it. Basically, this entire thing need to cut through using this curve. And again, it's a 0.15 cut and using 1/8 outside of this. And then I need the tabs because when you cut it, the material has to be attached. You cannot have it fall through because it's going to disappear on you. Right? I need to edit a tab. Add ramp, tab, edit tab. I'm going to put here, here, and here. Calculate. Okay. Reset. Visual tab. Okay, this is done. If I remove the tab, you can see what this parts look like. Let me remove the tab so you can, just for the sake of looking, for the look of it. Okay, I'm going to calculate and run. Okay, now this part is done. So here, as you can see, this CAM started with piece of material, and then you have to choose a different tool to machine this material and create a part. And anything can be break it down into that. And then I actually talked to a lot of mechanical engineer students, and then when they graduate with mechanical engineering degree, they don't know how to do CAM because CAM is traditionally taught in a trade school to blue-collar machinist. However, this amateur tool is so easy and convenient to use, anybody can learn it. So you can easily create a part, and then when you do that, as you can see, this whole part is done with a real thick materials and real tool paths and real tools, and then it will generate basically these lines. These are called G code, the 3-dimensional move of the machine. And yeah, sorry, my internet is a little slow, and I think I frozen a little bit. Can you still hear me, everybody? Can everybody still hear me?
Yeah, I can hear you. It got cut and like for I think a minute or so.
Yeah, my internet connection is a little slow.
Sometimes we hear you, sometimes.
Yes, so my internet is a little slow. Anyway, so yes, so that's how the things can be made. And of course, it's not that simple. And then as you go forward, you can see that you can communicate with me with this kind of software. And then if you want, I can send you some of the software I already bought. And then you can communicate with me with dimension, size, and then see how it's made. And you know how to do that, you hand these things to your school machinist. He immediately understands. And then when you design it, you also can realize some of the things cannot be made. Sometimes the student will design something, give it to machinist, and the machinist will refuse to make it. That's because they design something that's impossible, something like that, right? For example, a square, you wanted to have cut a hole that's totally square. That's just not possible. You cannot cut a square hole in it because the corner is infinitely small. Okay, so yeah, so that's everything. And if you have a question, go ahead.
Yeah. So you mentioned that this recording I can access it on YouTube.
Yes.
Okay, I just searched by your website's name, the Zoom AFM.
Yes, I'm sorry. I probably should make it easy to show. I'll show you the YouTube. Let me stop sharing and show you the YouTube channel. Give me a second. Yeah, this is basically YouTube /@nanoq. I should put a big link on the Zoom AFM. Promise to do it right away. And then
Okay,
it's going to be
great.
all the old presentations here. There's like 10 of these. Yeah.
Thank you so much. And also, like as you mentioned that you will send me this softwares. So if you have any version of the software, you can send me. And I don't know, like if Andrew's AFM the sample stage is like how it looks like currently. The sample heater I use with the Bioscope Resolve is kind of round, and it's kind of an insert that has ceramic layer outside it. And you mentioned something about water-based kind of heating, right?
Cooling, yes, heating or cooling, yes. Basically, if you wanted to do, let's say near freezing temperature to less than 80 degrees, you can easily make a water-based, water jacket base, which is make the whole thing very simple. Yeah.
Yeah, this one is actually plus 37 degrees Celsius for live cells, so it's higher.
Yes, yes. So what I think you can, of course, you can join. See, this is the website, weird trick. Go to website, you can get a free version of the software. The first, it allow you to design. It does not generate G code for you to machine, but that's what you want. Allow you to design. Just remember this trick matrix, and then you can start to draw things, whatever you want. Yeah.
Okay, great. Thanks.
And I have a design of this water jacket. Let's see if I can find it easily. Give me 1 minute. It was some time ago. I did that. Yeah, I'll send you later. It's a cut out of a piece of acrylic, and you have inner channel, outer channel, a water jacket, and then you pass the warm water through the outer jacket, and then you keep the entire thing warm at 37 degrees. And then if you put a rubber cover on top, which is also very simple design, then you can keep it at the moisture inside the cell and then not to evaporate. Yeah, very simple.
Yeah. Okay, thanks. If you find it, please send me. Thank you.
Yes. Did you receive the email I sent last Friday or some time ago about your instrument? You can the one of the drawback of the instrument, which is a 5420 model AFM, is its optical microscope is very small, and therefore you can try to see if it can see the living cell. If you have difficulty, we have to add a transmission illumination. And if you want to go further, and there's many upgrades you can do, and we can keep in touch. I'll show you how to do those.
Yeah, I communicated that to Andrew. It's basically Andrew's instrument, and because I am at Iowa State, it's like, you know, I cannot do anything about it. But yeah, we suggested, I forwarded that email that he can upgrade because it's his instrument now, so he can upgrade to 5500 as you mentioned in the email.
Yes.
To get a bigger optical microscope. So yeah, I think you will be working on that. We'll keep you updated.
Yeah. Let's keep in touch, and then yes, and then we can create some nice modules if you want. Yeah, it's not too difficult.
Yeah, great. Thank you. Thank you for all your suggestions.
So anybody have questions, please unmute and ask me.
Hey, Song, Jason here. This is adding to my Christmas list, I think, for my wife. It's pretty cool stuff.
Yes.
Question, what kind of little mini CNC router do you have?
I have, let me see if I can find it.
As you were talking, I started Googling mini CNCs here.
Yeah. So it's gonna be little machine shop. Let me show you what do I have. Okay, I don't have a commercial one. I have a modified one. This is this is a stand-up. There's two different kinds. There's like gate type, and this is vertical type. And I have a vertical type because it gives you much higher torque, so you can cut metal. And then I have a friend who modified it into a CNC. So this is the original machine, but then you could go eBay. There's tons of these. Let me see. Desktop CNC. Yeah. So there's tons of these. So let me show you this one's so cheap. The problem of this is very small. It does not have torque. It has a very high speed spindle. So you can do plastic easily. Probably cannot do metal, and because your cutter is very small, it does not move fast enough. You have to push very slowly. But you know, you can start with something like that. It's a little toy, and then it's yeah. Be careful and protect your eyes, and other than that, it's fun to play with. That here's part. See this box? Those are the meals you can buy from eBay, and pretty cheap. Yeah, and then after you break a bunch of tips, and you will realize what kind of things you have to pay attention to, and so on and so forth. This is, these are all a little bit less lack of torque. And see, this is a gigantic one, $5,000. This is a very, very big one.
5-axis there.
Yeah, 5-axis is a little too much. All I need is a 2.5D is good enough. And when you increase complications, you increase percentage of failure. I have lots of failures. My failure rate is 50%. I'm not a professional, but again, still, it's a lot of fun to do this. Yeah, these are a little too cheap. A good one, if you are building a workshop, is what we call Tormach. This is a very good one. Yes, this is a Tormach. Tormach 1000 is $25,000. The reason this is a good one is that this is the precision and the torque and the things you can make is industrial scale, but it uses regular household power. It does not use three-phase. So I have a couple of friends. They have one of these at home. They have 4400, 1000, and 7700. This is a different kind of model. It's basically small, medium size, and large size. A small size, obviously, is lower cost. And you can find those used ones. See, this one is $10,000. This is kind of small. And this one's $6,000. And they say there's some damage. So, you know, if you know some machinists can fix it, that's a good deal. Yeah, this can literally, this is my friend Ryan Murdick. He used this to build his ultra cryogenic AFM at home. That's how he built his business. I mean, he started to learn these things actually at the same time that I did. And he went much deeper into the technique and skills of making high precision parts. Yeah. So this is like upper end of the desktop CNC is Tormach. Okay, if we were running out of time, running out of questions, thank you for your time today. And if you have extra questions, I will stay here for 10 more minutes and then we can chat. And thank you for your time. See you next week.